Hello, my name is Sergey Vedasov, and I participated in the 2012 SURE program. So like in the 2011 SURE program, I worked with Professor Gabor Oros of the University of Michigan Department of Mechanical Engineering in analyzing the circular traffic model as a means of looking at autonomous cruise control systems. Unlike in 2011, most of my work this year was concerned with doing the nonlinear analysis for the model, which is based on the linear analysis of the model that we did during 2011, last year. So before going into what we did this year, I would give a brief recap of what this model is, how it was formed, and as well as the linear analysis on which the nonlinear analysis is based. So first of all, the reason for these autonomous cruise control models, like the circular traffic model, is the advent of autonomous cruise control systems in vehicles. They are becoming more common. And what this system basically is the vehicle has sensors that sense the vehicle's velocity as well as the position from our vehicle to the next vehicle, which is called the headway, as well as the relative velocity to the preceding vehicle. So the sensed information can then be used to actuate either the brakes or the engine to provide adequate torque and accelerate or decelerate the vehicle so that desired velocity and desired headway distances are achieved. Of course, this seems very nice because then the car can basically drive itself without the involvement of the driver on a single lane road. So this will create advantages to reduce driver mistakes such as collisions and inconveniences such as traffic jams. However, there's also some disadvantages in the sense that this system can become unstable, and then when it becomes unstable, collisions and traffic jams as well as inefficiencies in the traffic system can occur. So it's very important to analyze these systems before implementing them. So in this presentation, I'll first go through the development of the model and then go through the linear analysis parts and the important parts of it that carry on to the nonlinear analysis, which we would then examine for results when the system is unstable. We would then examine the possibility of simplifying this nonlinear analysis because it's a very complicated procedure by using some techniques we took a look at from last year and this year. At the basis of our analysis would be the circular traffic model. This traffic model is pretty self-explanatory, and there's a good illustration from MIT. Over here you get a single-lane circular road with some cars traveling on it, and each car is equipped with an autonomous cruise control system. So each car is capable of sensing its own velocity as well as the headway in front of it to the previous vehicle and the relative velocity of it compared to the previous vehicle again. So based off this model, we get two equations for each car to describe its motion. The first one is trivial, and it's basically saying that the velocity is the time derivative of position for each car. But the second one is the equation for the acceleration, and this is basically where the cruise control system comes in. So you see that the acceleration depends on the headway distance denoted by h, as well as the velocity of the vehicle and the relative velocity or the time derivative of the headway of the car. So from this equation, we can see that the acceleration of the vehicle would positively correlate with the increase in the relative velocity, because if we see that the car in front of us is traveling faster, we would tend to also travel faster. Also, the acceleration decreases with the velocity of our car because if we travel faster, we want to be more cautious and tend to slow down. Now, there's also a dependence on the headway, like I previously said, and this dependence is expressed by something called the optimal velocity function, or v of h, over here in the brackets. So the v of h in detail is the optimal velocity function, and it states that if a driver sees a given headway or a given distance in front of him, he will travel at a certain desired velocity. So for each distance, there's a given velocity. At a lower threshold, h stop, if a driver has headways below that threshold, then he would tend to stop the vehicle and the desired velocity is 0. At another higher threshold, h go, if the driver gets a headway above that distance, then he would tend to travel at the maximum allotted speed on the freeway. In between these two distances, we can have a monotonous increase of the function from 0 to the maximum allotted speed. This can be done either in a piecewise linear fashion, as the graph on the top right, or in a nonlinear fashion like this trigonometric function on the bottom right corner of the slide. So now that we have our model, we can do some linear analysis with it. So we have, in general, n cars and 2n equations. And first of all, to do any sort of analysis, we need to figure out what the equilibrium of the system is. And for this system, it's when all the cars are traveling with the same distance in front of them, which is going to be denoted as h star. You can get this distance by taking the length of the road, subtracting the lengths of all the cars, and then dividing that by the number of cars. So all of the cars have the same headway, but also all of the cars have the same velocity at equilibrium, which will be denoted by v star. And we can get this by plugging in this h star that we got earlier into the optimal velocity model. So once we know our equilibrium, we can then take our first-order partial derivatives in order to approximate the system as a linear system. And we get three parameters, f, g, and h, which again depend on the aspects of the sensors and the control modules in the car. So a good way to analyze a linear system would first be to write the characteristic polynomial or characteristic equation of it, which will give us the eigenvalues of the system for given parameters, or in other words, it will dictate its stability. So after analyzing this characteristic polynomial, we observed that the system would remain stable, so the equilibrium would be stable, as long as f is less than a certain critical value given in terms of gh and the number of cars. So this particular stability switch is called the supercritical Hopf bifurcation. In this bifurcation, at first, when the f is below the critical value, the equilibrium is stable. But as we increase f through the critical value, it becomes unstable and large amplitude oscillations occur. This can be readily shown in the graphs on the right, which are 3D phase plots of the velocities of the cars. So same will actually be true for the headways, but we just couldn't plot it in 3D so that you can see. So for the first graph, f is below the critical value, and all the cars would converge back to the equilibrium velocity even when they're perturbed. But once the f value would increase beyond critical f, you get these large oscillations, and the origin of the system is unstable. So now our linear analysis told us where is the equilibrium of the system stable or where is it unstable. It doesn't tell us anything about those oscillations that we experienced when the f gets to supercritical values and the system becomes unstable. In order to determine that, we have to perform some nonlinear analysis. Well, first of all, we have to do this because, again, the oscillations tell us a lot about the system. Knowing the amplitude of these headway oscillations and velocity oscillations, we can predict whether collisions or traffic jams are going to occur. As well, it may give us a quantitative estimate of what it would take to fix the system once it's gone unstable. So one can adjust these parameters for the system to become stable once it's unstable. So in order to perform this nonlinear analysis, we have to first improve our approximation of the system by including up to the third partial derivatives. So since the only nonlinearity in this system is that function v of h, the optimal velocity function, what we do is we take derivatives with respect to xi plus 1 and xi, which are the positions of the vehicle we are in and the vehicle ahead of us, because h is defined in terms of those two positions. And in between the second-order derivatives and the third-order derivatives, there's only a sign change because of the chain rule. So now that we have improved our model, we can write our equations around the equilibrium. Again, you have two equations for cars, but now the equations are in terms of the perturbed variables. That's where they have a tilde on top. So these perturbed variables are just telling you how far away from the equilibrium you are. The perturbed position is how far away from the equilibrium position you are, and the perturbed velocity is how far away from the equilibrium velocity you are. Now we have to do some nonlinear analysis, first of all using a coordinate transformation using the eigenvectors of the system. After that, we get into nonlinear techniques such as quadratic manifold reductions and near identity transformations, which will help us to reduce this system into a level which we can analyze. So we reduced our total system into one complex differential equation, which gives us the information about the oscillation of this complex variable. We can scale this back then using the joint eigenvectors of the system in order to get the oscillations of the headways and the oscillations of the velocities. So it actually turns out that the amplitude of the headway oscillation, as well as the amplitude of the velocity oscillations of the vehicles, would be directly proportional to the square root of the difference between the value of f the system is in and the critical value of f. So an important feature of this equation is the constant, which we determined from the original equations by scaling to be the equation on the bottom. And as you can see, even though it's big, it's in terms of the parameters g and h, as well as the nonlinear parameters m and r. So once we get this estimate, we of course have to compare it to something we do know. And for that, we used a computer simulation using a fourth-order Runge-Kutta code that we developed to get oscillations for a given parameter f in a system. We conducted 2 case studies in which the h parameter was set to 0.5 and the g parameter was set to 0, as well as the case where h was 0.5 and g was 0.05. And in both cases, actually, the analytical estimates shown by the black line and the numerical results converged quite well near the bifurcation point, so near the start of the oscillations. There is some divergence in the regions where the f is very high, as you can see for both cases, but again, the work is an estimate. It's a better estimate, but an estimate nonetheless. So once we validated our estimate, our analytical estimate for the amplitude of oscillations, we can do some analysis of what makes the system more stable. So first of all, we can rewrite our equation in this slide over here in terms of the equilibrium headway rather than the critical and f value, because the two are related by the first derivative of the acceleration with respect to h. So once we do that, what we can do is we can plot our amplitude of oscillation with respect to the equilibrium headway for both the cases when g equals 0 and the cases when g equals 0.05. So as you can see, not only does this relative velocity sensor, which is responsible for that parameter g, makes the linear stability better, which we can see by seeing that the range of the stable equilibrium is increased with the addition of g. There is much smaller region where oscillations occur with the addition of the parameter g. But also that the oscillations at where the parameter g is present, so in the bottom 2 graphs, are much smaller than the oscillations where g is not present, which is in the top 2 graphs. So this is for the first time we could analytically show that adding this relative velocity sensor and control model would benefit both linear stability and nonlinear stability of the system at supercritical values. So of course, this linear analysis was complicated. That's why it's not oftenly done to a system. So what we wanted to do is use a similar technique that we used in 2011 to analyze the system on a linear level. What we did back in 2011 was take a look at our system and block diagonalize it using the eigenvalues of the Laplacian matrix. What this basically does is reduce a large system, such as P, shown over here, to small subsystems shown as A, B, C, and all the information from the subsystems can be extracted. And it's the same information that comes from the system, just with less work. So we want to employ the same techniques when dealing with the nonlinear terms of the equations to break it down into subsystems and analyze it separately while gaining information such as the amplitude of oscillations. This is beneficial because if this is true, we can not only do this for the circular traffic model, but maybe other network models that we have. So that concludes our presentation, and thank you very much.